Hello, so it's come to my attention recently that there is a little confusion in the acid base lab based on the instructions and the semantics and the use of the word calculated. So this video is to help to try to explain that and hopefully make it less confusing. So the first data sheet has the data from the pH meter. So this is for our four HCl concentrations. These are for the four acetic acid concentrations. And this is measured clearly means data from the pH meter. Now, theoretical pH means what would the pH be theoretically from these given calculations over here. So this column, these calculations are all theoretical, and we calculate them from these initial concentrations. So as you guys know, since HCl is a strong acid, the concentration of hydronium at equilibrium is the same as the initial concentration, because 100% of these HCl molecules do the dissociation or the reaction with water to make hydronium. So calculating these theoretical pHs is quite easy, right? For instance, 10 to the minus 4 minus the log of 10 to the minus 4 is minus 4, which is 4. Okay, then when you get to the weak acids, the pH is still equal to minus log of H plus at equilibrium. However, that's not the same as the initial concentration of acetic acid because this is a weak acid. So we have to use Ka to get the hydronium first, then take minus the pH of that number. So if you recall, it's this sort of standard setup for a Ka problem where X is equal to the concentration of hydronium, and the pH is just minus the log of that X that you get. Now, the first two have a percent ionization of less than 5%, so you could do the simplified calculation. And remember, that means you ignore this minus X, and therefore X is simply the square root of Ka times the initial concentration. But these two have greater than 5%, so you have to use the quadratic formula. But once you get, however you get X, it's simply pH equals minus the log of X. So I think these first two parts are pretty straightforward. Here's where it gets confusing, right? What do we mean by calculated? So calculated Ka of acetic acid based on the data. That means they're using the word calculated to mean experimental in this case. So we're going to use the pH data that we get here to calculate the hydronium from the data and plug into the Ka expression. Now, by the way, the literature Ka is given in the lab, and it's the same for all four of these, right? So what the idea is to use these pH values, get the hydronium from those, 10 to the minus pH, and plug it into Ka and see how close we come. So on the next slide, I will give you an example of that. Okay, so here's an example. The calculated Ka of acetic acid based on pH data. So for the first concentration of 0.10 mole per liter, let's say that your pH experimentally came out to 2.92. So what I'm saying is this is an experimentally determined measurement from the pH meter obtained in the lab. If you're doing the video lab, I believe this corresponds to the recording I made in Blackboard. So the pH we know is minus the log of H3O plus. So H3O plus is simply 10 to the minus pH. So this H3O plus is calculated. They use the word calculated in the data table, but they really mean experimental. So this concentration would be 10 to the minus 2.92, and this is the value we get. So now we're going to get Ka from this experimental data. Now recall that Ka is equal to the hydronium concentration to the first power times the acetate concentration to the first at equilibrium, divided by the equilibrium concentration of the molecular form of the acid. So if we let X equal the concentration of hydronium, as we always do in these calculations, Ka is equal to X times X, X times X, divided by the equilibrium is the initial minus X. So the initial concentration is 0.1, right? That's right here. X times x is x squared. Therefore, our experimental Ka is x squared over 0.10 minus x. So let's look at the 0.10 minus 0.00120. I don't have to do this on my calculator because there's no number in this decimal point. These are insignificant when you add them together. The fly on the hippo's back. So it turns out that this is 0.10 in the denominator. In the numerator, x squared is 0.00120 squared. So we get Ka calculated, which means experimental, is this number. Now, if I, because the initial concentration here only has two significant figures, I would round that off. So the experimental or calculated Ka I get is 1.4 times 10 to the minus 5. And you can see that's not too bad. It's pretty close to the literature value. Are you guys with me? So in this data table, calculated is used very clunky. It's used as calculated from the experimental data. Now on the next page, for the pH of salts part of the experiment, there's only one calculation that you have to do, and it's here at the end, calculating K hydrolysis for the 0.1 molar ammonium chloride based on the measured pH and equation 17. So I'd like you to just see the handout that I provided in Blackboard that goes through that calculation. Okay, you guys with me on that? So that's a standalone thing that's sort of separate. What I want to jump ahead now and talk to is how the word calculated is used here. All right, so in the buffer solutions, here the word calculated pH means theoretical, not experimental. So they're using the word calculated in a different way. I guess one may argue the semantics that they are calculating the pH from the initial experimental concentrations. So I guess in that sense you could twist and turn your semantics into saying it is experimental, but it's not from the measured pH, and that's the important thing. Calculated here means theoretical, as I went through in the handout, not experimental. So this measured pH that you get here from the meter, you are not going to do any calculations with this column. You're simply comparing this number to this number to see how well your buffer worked. Okay? So for the strong acid, if we assume distilled water is perfectly neutral, which is an assumption, and has a calculated pH of 7, the concentration of hydronium would be 10 to the minus pH, or 10 to the minus 7 moles per liter. But for the buffer, it's a little bit more complicated. So again, let me go to the next slide and go through one example for you. So for the buffer solutions, the first thing we're going to do is get pH. Then you'll get the theoretical hydronium. So first use the Henderson-Hasselbalch equation to get the calculated pH from the initial concentrations. So this exactly follows the buffer calculations handout, and I go through this in great detail verbally in the video. But see, here's where the confusion comes in. Unlike the previous page, here calculated means theoretical. It's not from the experimental pH measurements. So once you have the pH from Henderson-Hasselbalch, you simply get the theoretical hydronium as equal to 10 to the minus pH in each case. So I'll give you one example. So for the initial buffer solution that we make in the lab, Henderson-Hasselbalch gives us pH equal 4.7. Again, that's right out of the buffer calculations handout and part 2 of the lab. I'm not going to go over that here. But I'm just going to say is to get the theoretical H3O plus, what they mean is simply 10 to the minus calculated pH, calculated from Henderson-Hasselbalch. Both of these are theoretical, and that's what we come up with. All right, so in terms of the exam, right, out of all of this lab, the really important calculations that you need to know, you really need to know how to use Ka to get pH of a weak acid, right? or KB if it's a base. And in terms of the buffers, I usually don't have time on a 1 hour test to give a really complicated calculation. Generally, what we give is just using Henderson Hasselbalch to calculate the pH from initial concentrations. And that's mostly, honestly, those are mostly a Chem 1 test, right? I mean, if you weigh out a certain amount of sodium acetate in a certain volume, you have to remember your Chem 1 to calculate what those initial concentrations are. Okay, so I hope this can helps with any confusion over the semantics of how the word calculated is used in the pH of acids, bases, salts, and buffers lab. Cheers, good people.